Okay, good afternoon. Welcome to the next IOA Colloquia. Before I introduce our speaker, I would like to say, due to a couple of dropouts, we have still quite a few spaces for the dinner. So please talk to me. It's at 6:30 at the Old Spring. We are figuring out how to get there as of right now. Ask me after the colloquium. Otherwise, today we have Sownak Bose from Durham. Sownak did his PhD in Durham. I actually replaced him in his office because my supervisor wanted me to be as close to his office as possible. So Sownak was displaced to at the end of the corridor. I'm really sorry about that. And then after he finished his PhD at Durham, he went to Harvard for his postdoc, and then he returned back to Durham as a associate professor, where he currently also has the Future Leaders Fellowship, which I heard that it's going to be for the next few years as well. So please, Sownak, go ahead.
Okay, can people hear me okay? Brilliant. Thank you very much, Jan, for introducing me, and thank you for having me as your speaker here today. So I was in Cambridge about a year ago, and I spoke then about galaxy redshift surveys and large-scale structure and the galaxy halo connection. So I thought, for the sake of variety, I would talk about something very different this time, focusing very much on the small scales of the universe, specifically structure formation in the cold dark matter model. I want to tell you about some of the smallest galaxies that form in this cosmology and what it can tell us about the nature of galaxy formation, about the nature of dark matter, all the way down to the very smallest structures we ever expect to form in a universe made of dark matter. It helps to think about why we care about cold dark matter as this model of a particular interest. And I think the motivation behind this need not be labored for too long. I think it's always a great testament to a model where you can make observations of the very early universe, looking at, for example, the temperature fluctuations of the cosmic microwave background, find a model made of a handful of parameters that agrees with those data, and then by looking at gravitational instability and how that progresses over billions of years, also predicts the large-scale structure of the universe that looks like it's in good agreement with what we observe with galaxy redshift surveys. And so this connection between the very early universe and the late-time universe, from a theoretical perspective, is something that we have been able to do thanks to improvements in our ability to model nonlinear structure formation due to cosmological simulations. So the cold dark matter model, or models of dark matter, don't just predict the large-scale structure. They predict structures that form across a very large range of scales. And one way to understand how this happens is by looking at the very early universe, so measurements of the primordial density field in the form of what we call the power spectrum. So it's predicting, for a given dark matter model, what is the lumpiness of the universe in the initial conditions, going from large scales to small scales. And generically, it looks something like this, where power increases from large scales per unit wave number to small scales, meaning that there's more power on these small scales, and therefore these are the scales that collapse first. And depending on what you think the model of dark matter is, there can be a truncation to where this power continues to. So if you have a model of dark matter called warm dark matter, for instance, where particles are somewhat relativistic at early times, it induces a cutoff on this scale relevant to dwarf galaxies, which is why dwarf galaxies tend to be one of the great tests of models of warm dark matter and comparable ones. On the other hand, for popular models of cold dark matter, such as the neutralino or WIMP-like particles, this cutoff is on substantially smaller scales, where the characteristic mass of dark matter halos is of the size of the Earth, so about 10 to the minus 6 solar masses or so. And so in this cold dark matter universe, if you were to just sort of visualize what is the range of mass scales that you actually span, you have things that go all the way from the rich clusters of galaxies all the way to these Earth mass halos, so something like 20 or 22 orders of magnitude, which is quite exceptional. And what I want to focus on today is three particular regimes. So one, which I'll focus on here, which I call the edge of galaxy formation, which is where we think galaxies essentially stop forming because the dark matter halos become small enough for that. the edge of visibility, which is basically the smallest structures that will ever have a baryon in them of any type over the course of their lifetimes. And finally, going all the way to the very smallest scales, the edge of structure formation itself, which is where are the last dark matter halos and what are their properties. So it's an ambitious goal to achieve over the next 45 minutes or so, but I'll do my best to do this. So let me first start by talking about the very smallest galaxies in the universe. So one of the reasons that cold dark matter is a very popular model is that it is predictive about the nature of structure formation, even on very small scales, on very nonlinear scales. So this is an image from the Aquarius simulations, which shows the prediction for the cold dark matter model for the distribution of dark matter around a galaxy like the Milky Way, which would be at the center here somewhere. And surrounding it is a teeming populations of hundreds of thousands of subhalos of dark matter, which themselves could be the hosts of galaxies. Now, when one takes this picture and compares it with the distribution of the known satellites of the Milky Way, measured as a result of surveys like the Dark Energy Survey and Sloan and so on, you find that there's a mismatch in the number of objects. So this number 54 here is a bit outdated now, but the point being that there is a difference of several orders of magnitude between the number of known visible satellites and the number of subhalos of dark matter that orbit the Milky Way predicted by simulations. So if cold dark matter is the correct model of structure formation, or something approaching that anyway, the question you can ask is, why do most of these objects remain dark? So this is something called the missing satellites problem. And I think the answer to this is pretty straightforward. It's a result of well-known physics that has been known for a while. And so what what I'll try to do here is to motivate how this works. So let's say we have redshift on the x-axis and the mass of dark matter halos on the y-axis. The minimum condition required to actually cool gas in a dark matter halo is to exceed a certain threshold, which is a threshold relevant to atomic hydrogen cooling. So prior to the Epoch of Reionisation, halos that exceed a certain virial temperature will be able to cool gas and form stars. But when reionization hits at some redshift, what it does is that it raises the entropy of the gas and basically changes where that critical threshold is. And it basically sets a different locus. And the mass scale corresponding to this is sometimes in the reionization literature called the filtering mass, or the critical mass for galaxy formation. So it raises to about 20,000 Kelvin or so. So imagine, so that's basically the same curve. So imagine now you have a dark matter halo, which at the final day has a mass of the order of 10 to the 9, or a few times 10 to 9 solar masses. But its assembly history is such that at no point in its history it ever exceeds this critical curve. Then basically it has never had the opportunity to cool gas and form stars, and therefore this remains a star-free dark matter halo. And on the other hand, if you have an object whose assembly history is such that you reach the same final day mass, but at different points in its history it exceeds this critical curve, then you have had the opportunity sometime in the past to form stars. Okay? This is therefore a luminous halo. And this is physics that has been known for a while, and if one is facetious, you could actually say that this is the solution to the missing satellites problem has existed longer than the problem itself has. But what happens as a result of this is when you have cosmological hydrodynamical simulations that actually incorporate this physics, whereas the image of the local group, for example, in the dark matter distribution looks something like this, the image in terms of the visible galaxy population looks a little bit like that, okay? And so clearly already you can see that there is a difference in the number of dark matter halos and visible galaxies, and therefore you approach something resembling a solution to this problem. Now, studying this population of the really low mass galaxies, these satellites of the Milky Way, in great abundance is pretty challenging for hydrodynamical simulations because of the enormous computational expense required in both simultaneously capturing the Milky Way and these ultrafaints as well. So in my group, one of the techniques that we work on, which has been pioneered in Durham for a long time, is something called semi-analytic galaxy formation. And so it's sort of a halfway house between n-body only simulations and hydrodynamical simulations. The idea being that you create an n-body simulation that therefore gives you the entire growth histories of dark matter halos self-consistently. You then put in models for gas cooling, star formation, dust, the evolution of black holes and feedback and so on. And what pops out in the end is, well, nothing that looks like that, but a set of numbers that represent the galaxy populations relevant to this model, okay? And critically, the semi-analytic method allows us to statistically probe a regime, the regime of the ultrafaints, which would be well beyond the capabilities of current hydrodynamical simulations, at least to do at scale. So a couple of years ago, we looked into this problem of what is the assembly history of ultrafaints, or dwarf galaxies around Milky Way-like galaxies, in the context of the semi-analytic model. And what you can do is make a diagram of what the present-day stellar mass of these galaxies is, and on the y-axis, the fraction of this mass that has assembled prior to redshift 6, which in the case of this model, the blue one anyway, was when reionization is imposed. And if you just look at the blue curve, what you find is that there's basically two different populations here. A population of galaxies that have assembled primarily prior to reionization, which is basically the regime of the faint or the ultrafaint satellites, and those, the brighter ones, that have assembled primarily later on and know very little about when reionization has taken place. And I should stress that this is not just a hallucination of the semi-analytic model. This is, in fact, something that we tend to infer from the star formation histories of the ultrafaints around the Milky Way by looking at their resolved stellar populations. And in fact, the data seems to suggest a preference for star formation histories that are largely assembled by a redshift of 6 or so. So now that we understand where these satellites, or how these satellites are assembling their mass, we can actually do this process of counting them. Okay, and so what I'm showing here now is the luminosity function of Milky Way satellite galaxies. So you just count the number of objects by their magnitude or their stellar mass, and you bin them. The data here shows the inference of the total satellite population of the Milky Way made by Oliver Newton a few years ago, which takes the known satellites and then corrects for the observational completeness and predicts the total population. This looks a little bit different to how luminosity functions are often presented, because what I'm showing here is the differential number of galaxies per bin of magnitude rather than the cumulative. Now let's now overplot the predictions of the semi-analytic model, which we call galform, and see what it looks like in this space. And it looks a bit like that, okay? And what I should stress here as well is that in calibrating the parameters of this model, absolutely no aspect of the ultrafaint population has been used to fix the parameters of the model. The way we calibrate the parameters in galform is to look at the predictions of the field population of galaxies much brighter than the Milky Way satellites, and yet that same model is able to reproduce the distribution of the ultrafaints pretty well. And here too we see some evidence of this two-population nature of the ultrafaints that form left of this kink and the brighter satellites that are to the right. So you can actually run a bunch of numerical experiments to see how changing parameters in the process of reionization actually shapes the luminosity function of the Milky Way satellites and as well as its number. And basically what you find is that the two parameters that are most important, one is when reionization is happening. So basically how long galaxies can continue forming stars before the intergalactic medium is heated up. And what that does is basically it changes how many ultrafaints you actually have. So what is the normalization of this curve left of this valley which separates the pre- and post-reionization populations? Whereas this filtering scale, which is this critical mass that I was talking about previously, above which halos need to be in order to form galaxies after reionization, is basically what changes where this transition between the two populations is happening. Okay, so this is obviously a simple model. Okay, reionization is not just a two-parameter thing as it operates in the real universe, but this is one of the ways by which we can use semi-analytic models to at least understand how parameters or how physical processes are changing some of the observed predictions for galaxies. It turns out that reionization alone isn't responsible for changing the demographics of the ultrafaint populations around galaxies like the Milky Way. And in fact, the assembly history of the host galaxy, i.e. the Milky Way itself, can be similarly important. So this is something that we worked on a couple of years ago now and involved Vasily as well. And so what I'm showing in this diagram here is, again, the luminosity function of satellites, so number of satellite galaxies as a function of their stellar mass. And what I've done here is now split this into two populations. The green, or the whatever color that is, turquoise set is the ultraphanes belonging to Milky Way mass galaxies that assembled early on. So you select them based on their formation history, whereas the yellow correspond to satellites belonging to late forming Milky Way mass galaxies. So just differences in their merger history. And what you find is that there is a substantial difference in the number of objects that are predicted, particularly in the regime of the ultraphanes. In particular, it turns out that these early forming Milky Way-like analogs tend to have larger numbers of these ultraphanes, at least according to this model. So it's not just reionization that matters, or indeed the particle properties of the dark matter, which I won't talk about today, that determine the abundance of Milky Way satellites, but in fact, even things like the assembly history can matter significantly as well. And this actually makes it quite challenging to set very definitive constraints on the nature of dark matter using the populations of ultrafane galaxies, because there's many other things that can affect exactly how these populations look. So maybe a more general way to ask this question is, what is the physics in galaxy formation that is setting the properties of the dwarf galaxy population, okay, in a very general sense? This is, again, the sort of arena where semiotic models are really powerful, because what you can do is run tens of thousands of examples of the semiotic prediction under different assumptions of how we think galaxy formation works, and basically sample the entire space and try to infer from how these models respond to the input parameters to see how galaxy formation actually affects the properties of the dwarfs. So to do this, what we do is something called Latin hypercube sampling. So we have a model defined by a certain number of input parameters. So I'm showing 3 here, but actually we change about 11 different parameters of the galaxy formation model. And Latin hypercube sampling allows you to sort of fairly sample this high-dimensional space of parameters and basically use a very large number of input models. So the parameters of interest that we want to see how they influence the dwarf galaxy population in this work are parameters relating to reionization. Okay, so there's the redshift and this critical mass scale, which is expressed as a circular velocity. Clearly, something else that is important is how supernova feedback works. Okay, so the parameters associated with supernova feedback, of which there are 3, and I'll tell you how they're connected in a second. And finally, some parameters describing the nature of star formation. Okay, so I'm showing just a subset of things here. There's about 11 in total. And so the way this works is that in the model, dark matter halos are reionized at some redshift below this redshift of reionization if their circular velocity is less than some critical value. And finally, the way supernova feedback is modeled is in a very simple mass loading factor type way of measuring things. So you have a dependence, a power law dependence on how much gas and metals are basically ejected given a circular velocity, and it depends on a power law index and a normalization. So how do we assess how the model changes as we change one of these parameters in our thousands of simulations? So here we use something called sensitivity analysis, which is basically a statistical modeling technique. And what sensitivity analysis basically says that, say you have some model, y, which is some function of x, where x is a vector of a certain dimension, which is basically the number of input parameters that we put in. You can define the variance of this model with respect to the ith parameter by basically looking at how the expectation value of this model prediction changes as you change other things and leave this parameter fixed, essentially. So that defines the variance of the model with respect to the ith parameter. And you can then define something called a sensitivity index, where the first order sensitivity index, S sub I, is this variance parameter divided by what is the average variance of the model. And for deterministic models, such as in our semiotic case, all that changes when you run the model once or the next time is just how the input parameters change, and those are the only things that influence what the outcomes are. So if you run the same model twice with the exact same parameters, you will get the same results. So what that allows you to do is you can normalize these quantities in certain ways that allows you not just to measure what is the first order impact of a parameter on a prediction, but also what is the crosstalk between parameters. So what are the higher order interactions between them in shaping this prediction? So now let's revisit our luminosity function again. So this is, again, the satellite luminosity function of the Milky Way, but now shown in a very different way. The x-axis is now showing bins in V-band magnitude, or stellar mass equivalently. And now each pixel is colored by the value of this first-order sensitivity index. So it's saying, how does the abundance of galaxies in this bin of the satellite luminosity function change, or how sensitive is that to certain changes in the input parameters, which have clubbed together under reionization, star formation, feedback, and so on. And so pixels that are sort of yellowish or creamish colored basically mean that there is no effect on the luminosity function, whereas ones that are closer to blue or black are really strong determinants. And so what you find is that supernova feedback is the most influential process. And in fact, the power law index that goes into this mass loading in the feedback process affects not just the ultrafaints, but it matters across the entire mass range. And reionization ranks second. And it turns out that reasonable variations in how we model the star formation in terms of the gas consumption, timescales, and so on, make very little difference to what the satellite luminosity function does. So it's really supernova feedback and reionization that are the primary culprits here. You can now repeat the same thing, not looking at just the abundance of satellites, but some other property of this population, such as what are the metallicities of these ultrafaints as well, because that's something you can measure in the data. And so this is exactly the same diagram, but now showing what is the average stellar metallicity of these galaxies and how they respond to these parameters. And here, what you see is a rather different picture to what we had for the luminosity function, except for the fact that supernova feedback is, again, the most influential process, which makes sense because it controls how much stuff is blown out. But the reionization process, for instance, doesn't really have much of an impact in shaping what the metallicity distribution actually looks like. So what about higher order correlations between parameters? So how do different processes in the galaxy formation process actually influence these and how they interact with one another? So this diagram now shows, again, the same thing as I was showing you before, but just now showing you points instead of pixels. So the different colors are the sensitivity indices of the satellite luminosity function with respect to each one of these parameters. And again, you see that the parameter that is above most of the other ones is this golden colored one, which is the power law index of the supernova feedback. What we can now do is overplot the lines for what we call the total sensitivity index, meaning how much does this parameter depend on higher order correlations between other things, each of the other parameters. And you see, for example, for this gamma, which is the power law index, there is a gap, there's a big gap between where the first order index is, which are the points, and where the total index is, which is the solid line, meaning that it's not just feedback alone that matters to shape the satellite luminosity function, but rather the different parameters in the model are interacting with each other at second order, third order, and so on to give you what the final luminosity function looks like. You can repeat the same exercise with the metallicities now. Again, the power law index is the most sensitive process, so it's the points which are the highest. But if you now overplot the total sensitivity indices to this, actually the gap between the solid lines and the points is not as large, okay? Which means that it's predominantly the first order effect of supernova feedback that is affecting the metallicities of these galaxies. So that's one of the interesting conclusions that you can do with this kind of model parameter statistical analysis with semitic models. So the reason I focused on these two data sets, so the satellite luminosity functions and the metallicities, the reason behind this is that there's kind of a bit of a tension between them, okay? And to explain what I mean by this, you can do the following exercise. So I told you previously that this galaxy formation model is calibrated in a way that knows nothing about the ultraphanes, okay? Let's break that assumption and say, let me try to fit the parameters of the model so that we fit the satellite luminosity function of the Milky Way only, okay? And so when you do that, you get this yellow curve, which does an okay job in matching those data. And then we say, okay, what does this prediction now look like for the mass-metallicity relation for the Milky Way satellites? And what you get is something that is discrepant by maybe factors of 10 or more, okay? Well, if you invert that question and say, let's try and fit the mass-metallicity relation and see what it means about the satellite luminosity function, you now fit the metallicities well, but your agreement with the luminosity function, the abundance of galaxies, is completely ruined. Okay? And we can kind of understand why this happens. It's because the sign of the change of one statistic or the other with respect to any of these parameters is basically in opposite directions for how feedback works, for instance. So one way to visualize this is these things called Shapley additive explanation models, which is basically a machine learning thing, which tells you how a model responds to changes in input parameters. So I'm showing you the luminosity function on the left, the mass-metallicity relation on the right, focusing on one bin in particular, which is in the regime of the ultraphanes. And I'm just showing you the top 5 parameters that are the most influential for the predictions on this scale. And the way to read this is that blue colors means that I have taken that parameter and increased it to a very large value. Yellow means I've taken that parameter and reduced it to a very small value. And being on the positive side on the x-axis means it has increased the prediction of metallicities or abundances of the number. Negative means I've decreased it. And the main thing to take away, if it's a complex looking thing, is that the colors are basically inverted in terms of what the directions are, okay? And that is to say that these two data sets are actually pulling the parameter space, particularly related to the supernova feedback, in opposite directions. And one way to see this is that imagine you took this gamma, which is a power law index in your mass loading, reduced it to a very small value. What that does is that it weakens supernova feedback and therefore enhances the metallicities of the galaxies because fewer things are blown out. But that actually ends up decreasing the number of ultraphanes, which sounds counterintuitive, but it decreases the number of ultraphanes because the reduction in the strength of supernova feedback actually allows the galaxies to grow larger. Okay, so they actually move from left to right in the luminosity function as a result of this. And so this is, I think, an interesting way to consider model fitting, which is considering multiple data sets of these kinds that potentially pull your parameter space in different directions. And in this case, it turns out it's quite difficult, actually, to fit these two simultaneously without going into a region of parameter space that breaks all the other agreements that the GALFOR model was initially based on. So this suggests that clearly there's potentially some missing physics or incorrect assumptions that's going on in this model, which we can speculate on. So I think that that's a really interesting thing to think about as we get better data and more amounts of data, not just for the Milky Way satellites, but indeed for things like the high redshift galaxy population, where galaxy formation might proceed very differently to what it does for local galaxies, to seeing what we can actually end up learning about the physics of galaxy formation by looking at these kinds of ways of considering theoretical models. So much for the small galaxies, but what about the baryon content of even lower mass dark matter halos? Okay, so I want to focus now on the regime going from a few tens of millions of solar masses to about 1,000 or even 100 solar masses or so in dark matter halo mass. So this is a challenging regime to consider when it comes to understanding, how do baryons actually trace the dark matter, because clearly this requires very specialized sets of simulations. So this is something my now graduated student Haonan Zheng did as part of his PhD project. So where he took very high resolution simulations of smallish patches, so these are patches of the size of 2 megaparsecs or so, and ran this multiple times, once with just dark matter, once with dark matter plus non-radiative gas, and once with dark matter plus gas that is able to cool, and then also adding an ionizing background. And what you notice, looking at the top panels and the middle panels, is that the dark matter distribution in all three variations of the simulation don't really change. That makes sense, right? The addition of the gas doesn't substantially change the dark matter distribution. But if you look at where the gas is, okay, the simulation has just non-radiative gas, which is the top panel. There we go, over here. The top panel in this row, you see that the gas follows the dark matter distribution, and in fact, the largest dark matter halo here still has some gas in it, whereas once reionization is included, the baryons are completely evacuated out of there. So these dark matter halos don't contain any gas in them at all, okay? They become completely unbound. It turns out that this actually has an effect on how the dark matter halos themselves grow. So this is now focusing on two different bins of halo mass, so about 10 to the 6.75 and 10 to the 6.5 on the left and right respectively. And these curves are showing the mass growth of dark matter halos as a function of redshift. The white curve is showing the case for the dark matter only simulation, and the yellow curve for the simulation where there's only non-radiative gas. And you see that the inclusion of non-radiative gas has no effect on the assembly history of the dark matter halos. The blue curve, which now shows the simulation where you have reionization as well, behaves exactly the same prior to reionization, so the curves all overlap, but then diverges at redshifts less than that. And basically what's happening is, as a result of the baryons now being evacuated out of the potential wells, you basically slow down the growth rate of the dark matter halos, because in the other simulations they would have had dark matter instead, or the baryons instead, but now those have been removed. So you have changed the structure, and that affects how the halos themselves assemble. And indeed, you can see that also in the density profiles, where the densities are lowered by about 15 to 30% or so. So if you then look at this question of what is the baryon content of dark matter halos as a function of mass in these really low mass regimes, so this is showing the baryon fraction normalized to the cosmic average for objects of different mass. Prior to reionization, no matter what you do, they all kind of follow the same thing. The non-radiative simulation and the reionization-based simulation have the same baryon fractions. But then once reionization hits, the gas all becomes unbound to the point that you basically have no baryons in a very large mass range of objects here. So forget about galaxies in the first place. Many of these objects don't contain any baryons of any sort at final day, at low redshifts. In fact, you can even write down a theoretical model which tells you that below a certain mass scale, the gravity of these halos will never be enough to overcome the pressure of the baryons to ever see a baryon in their lives, okay? So these don't have baryons, so what else can we learn about objects of these extremely small masses that we don't already know? So are they at all interesting of any kind if there's nothing visible associated with them? And I will argue that, in fact, the interest is substantial. So this takes me to this third section, which is what is the structure and properties of the very smallest objects in the universe, going all the way down to the Earth mass dark matter halos. So if there's anything that we know about dark matter and dark matter halos, well, to sort of quote a popular adage, right? So there's three certainties in life: death, taxes, and that simulations predict NFW profiles, right? And so what that means is that if you take objects of different masses across rich clusters all the way to dwarf galaxies, and you measure their densities as a function of radius, you find this universal shape, which is that they have slopes of -1 right in the center, slopes of -2 in the middle, and slopes of -3 in the outskirts. So the question you can ask is this actually true of objects all the way down to the Earth masses? Okay. So this is clearly going to be a challenging thing to answer, right? Because these are exceptionally small things. So trying to resolve them in cosmologically representative environments is going to be really difficult from a computational perspective. So when people have tried to do this in the past, what they have tried to do is, okay, we need extraordinary resolution to be able to see 10 to the minus 6 solar mass objects, right? So let's just simulate very, very, very tiny volumes, okay? So this is some work by Raul Angulo and collaborators, which looks at a cosmological, a region of size 20 kiloparsecs or so. So this is clearly not cosmologically representative in any sense. But when you run a simulation like this, you can't actually run this to redshift 0. And the reason for this is that at very early times, at like a redshift of 30 or so, the characteristic nonlinear scale in the universe actually becomes comparable to the size of the simulation itself, meaning that the assumptions that go into building the initial conditions are no longer valid. So you have to kind of stop it at these higher redshifts. But when you extract the dark matter halos from these simulations, you find something rather odd, okay? So here are 6 different examples of halos that have been extracted from these simulations at early times. The different colored curves are measurements of that same density profile at different redshifts. And what you notice here is that the density profiles don't really look like NFW at all. So it doesn't have this 3-sloped feature. In fact, it's like a single power law with a slope of around minus 1.5, okay? And what is interesting about them, so they're very cuspy in that sense, but what's interesting about them is that this structure is created immediately after the initial peaks collapse, okay? So it's not something that has built up over time, it is immediately formed. So these things are called prompt cusps, okay? They form promptly and they're very cuspy in nature. So is there now a tension between what we think is the universality of profiles and what these things are showing at high redshift? So to try and understand what these dark matter halos actually look like at present day, like I said, you can't just run a normal cosmological simulation because of the enormous resolution requirements. So what we do is use something called a zoom simulation technique, okay? Which is where you start off with a big volume of several hundreds of megaparsecs. So this is a variant of the Millennium simulation, but with updated cosmological parameters. So here you have all the large-scale structure of the universe. The characteristic mass scale is about 10 to the 14 solar masses or so. You then pick a region of interest shown in the circle and put all your computational power in this region and degrade the resolution outside it. Okay, that's called the zoom technique. And what you get is something that looks like this. Now the resolution is better, so the characteristic mass scales we resolve are 1,000 times smaller, about 10 to the 12. You pick another region in this, do the zoom again, and you get something like that. Now the characteristic masses are 10 to the 9 solar masses or so. You can see that the environment is getting emptier and emptier because we choose slightly underdense regions to enable this to actually work. You pick another region, resimulate that at higher resolution, and now the characteristic mass scale is 10 to the 6, and you keep repeating this process again, and again, and again, and again, and there was another time, yeah, and again. And until you get to this point, where now the characteristic mass scale of halos resolved in the simulation is 10 to the minus 6 solar masses, the edge of structure formation in cold dark matter itself, yet still embedded in a fully cosmologically representative environment. So to give you a sense of what this looks like, the first 3 levels of simulation that we do, the particle mass we reach is about 1,000 solar masses. So any n-body simulation paper you will see that quotes a mass resolution of 1,000 solar masses will say we have really high resolution. By the time we get to the very last layer of simulations, an individual particle has a mass of 10 to the minus 11 solar masses. Okay, this is about the mass of the atmosphere of the Earth. And it's quite extraordinary that you're able to actually do this using new technological inventions that would not have been possible a while ago. So what that means is that you can now actually measure the complete halo mass function of a cold dark matter universe, going all the way from the very largest objects to the very smallest objects. So when you stitch together these levels, you can see the number of dark matter halos as a function of their mass on the x-axis. The first 3 levels give you these curves here. And then when you stitch all of these levels together, you build up the entire mass function like this. And it looks kind of like a power law all the way throughout. So now you have a halo mass function that spans around 22 orders of magnitude in the same cosmological environment. So if you asked me 20 years ago, would this have been possible? I would have said, I have no idea, I'm 12 years old. But this really is a testament to what can be achieved using our modern generations of computers and new techniques for doing simulations. So what does this tell us about the universality of halo structure? This figure here shows radius on the x-axis, and the y-axis doesn't show density, but it shows the logarithmic slope of the density profile. So the NFW prediction will be the dotted curve here, or the Ionasto model, which is just another variation of that in the dashed line. And the stacked profiles, basically, of objects from each of these different levels are shown with the different colored curves. And they all more or less trace the NFW form pretty well. Okay? So seemingly, the universality of halo profiles is well preserved. And certain people in Durham will not be very upset about the fact that universality is broken. Okay? But is there still now a tension with what the high redshifts are telling us? Okay? So to answer this, we can try and think back to what is actually happening when the first structures are forming. Okay? What does theory tell us to expect? So when an object collapses out of an initial peak, you can use models of self-similar collapse and peak collapse and spherical collapse models and so on. And what it tells us is that you can consider the collapse of certain shells of mass that then rebound and virialize and so on. And you can use the assumption of self-similarity to say that, okay, the behavior of one shell is basically the same as another shell, just rescaled in time, so on and so forth. You can work out the equations of motion for each of these radial shells and make a theory prediction for what the radial density profile should look like. And when you do this under the assumptions of self-similar collapse from a primordial density peak, remember these Earth mass halos are formed right near the cutoff of the power spectrum because they are the earliest generation of structures that are formed. You can get an analytic or semi-numerical prediction for what the density profile should look like. And it's basically that the density scales as r to the minus 12 over 7, which is not quite the minus 1.5 that I was showing you before from the simulations, but it's not too far off either. So how do we then study the formation of the dark matter halos and understand how these are transitioning from the initial peaks that they arise out of into the final day objects that we look at? So this is some heroic work that's being led by one of my PhD students in Durham, Yu-Chan Wang. And so what she's doing is, well, she recognized very quickly it'll be kind of unfeasible and impractical to study the formation of these Earth mass objects right near the cutoff scale for cold dark matter because of just how demanding the resolution requirements are. So instead, you can bring this cutoff in the power spectrum to you instead by just artificially truncating what the initial conditions are at different values of the wave number. That's what's shown in these different colored lines. Okay? So these basically show very hot or warm dark matter-like models going down to cooler models from left to right. Okay? You can then simulate the formation of dark matter halos of different characteristic masses so that you're basically seeing how does an object of a given mass respond to changes in the initial conditions depending on where it is relative to where the cutoff is. Okay? So you artificially cut off the power spectrum, and therefore you change where the peaks, the initial primordial peaks are collapsing out of, and you look at where the halos are actually forming. Okay? So to give you a visual representation of what this might look like, this is now showing 3 examples of the same dark matter halo. Okay? So the same initial conditions, except for the fact that this primordial power spectrum has been cut off on either very low wave numbers, i.e. large scales, or very high wave numbers, i.e. small scales. So there should be more small scale structure on the right than there should be on the left. So when you run this forward, you get something that looks like this. You see the initial filament that has collapsed. You have the main halo that is forming inside this filament. It then accretes mass and material over time, and there's other subhalos around it. And it's formed some kind of virialized structure by redshift 0. On the other hand, if I showed you the simulation where there is an absence of small-scale structure, you'll again get a very filamentary structure forming initially, but this halo itself forms promptly, but there's very little other material for it to actually accrete in its lifetime because there is just no power on these scales. So you can ask the question, where does the mass associated with a dark matter halo actually come from? Right, okay. If we look at an object at the final day, where is its mass coming from? Is it coming just from the initial peak from which it collapses, or from surrounding material? So that's what this figure here is showing, which is a bit complicated, but I'll try and explain this. So from left to right, we have the same object, okay, but just, again, different situations on where the primordial power spectrum has been cut off on. It's been cut off on large scales on the left or very small scales on the right. What we do is look at the dark matter halo at the final day at redshift 0. We take its particles and map it all the way back to the initial conditions. So the coordinate on the x-axis is basically the location of the particles associated with this final day object as a function of their distance from the peak. And the points inside, and the y-axis is a measurement of the linear density that these particles had in the initial conditions. And the particles, the different colors, show you the particles associated with the main halo that have collapsed out of the peak itself. And the other colors are the additional substructures that this object accumulates over its lifetime. Okay, so because the truncation of the power spectrum is on very small scales in the right-hand side, you have more other colors in that one than you do in the ones on the left. So let's see what this implies for the evolution of the dark matter density profile over time. So the main thing to really focus on is the third column on the right, okay? And each row shows basically 3 different time steps or 3 different redshifts in the evolution of this particular dark matter halo. And what the figures show is on the x-axis is distance from the center of the dark matter halo, and the y-axis is the density multiplied by r to the power of 12 over 7. So if things are indeed like these prompt cusps, then in this space they should look flat, okay, because it's multiplied by that term. And now the lines have been split up into the particles that were associated with this initial density perturbation itself, the peak from which the main halo originates, and the other mass that the halo accumulates over its lifetime through accretion and mergers and so on in white. And what you notice is that this red line, which is the initial peak particles, are flat. And that kind of more or less stays the case throughout the evolution of the halo. So indeed, these are following the predictions of this prompt cusp formation. But the white curves, which is the mass that is accumulating on the outskirts of halos, is actually building up a different shape. And of course, the final density profile is going to be the summed contribution of both of these. And in fact, the white is what converges further towards the NFW-like shape over time. So these prompt cusps are actually buried in the centers of the dark matter halos on small scales, whereas what we see as NFW profiles in simulations all the time at present day are actually the result of the halo accretion history on the outskirts. Here's a real example of one of the cases that Yu-Chan studied. So this is showing how a merger between a halo and another object actually builds up the NFW profile. So left to right shows time. The middle panel shows you the particles associated with the main peak or the main halo itself only, whereas the bottom row shows everything else that eventually merges onto it. And the top row again shows this density multiplied by r to the 12/7, okay? And the solid line in this case is showing the density profile of this middle row, i.e. the particles associated with the primordial peak itself. And the dotted lines are everything else that merges onto it. And the NFW profile in these units basically looks like that, okay? And as you can see, as time progresses, these peak particles, or the things that most closely resemble self-similar collapse, are the ones that remain kind of flat in this space, maintaining this prompt cusp prediction that we not only see in simulations, but also can predict through models of spherical collapse, whereas the remainder of the particles which contribute the bulk of the mass on the outskirts is what transitions towards NFW. So that allows you to actually build up a picture of where NFW profiles come from, okay? Which is that when dark matter halos collapse out of a primordial peak, you start off with a prompt cusp. So the true density profile, in quotes, at the very center is this prompt cusp, which looks flat in this space. and they formed immediately after the collapse of the halo. And then objects throughout their histories can experience a variety of different things, mergers with other objects, interactions with other objects, something somewhat insidious that happens in simulations, which is accretion of artificial fragments. Sometimes that also happens. But all of these have the effect of taking this prompt cusp and transitioning it into an NFW profile at late times, with the prompt cusp still being preserved right at the very center, far below the resolution scale of most n-body simulations. So why is this universal? Okay? And I think the reason for this is, again, something we have understood for a while, is that the density profile is tied inextricably to the assembly histories of dark matter halos. Okay, so this is some work that Aaron Ludlow and I did a few years ago, but several other authors have shown this in a variety of other guises. But it turns out that in a cold dark matter model, it doesn't really matter what the initial power spectrum is or what the cosmological parameters are. If you take the assembly histories of dark matter halos and you just write them in some funny unit, so it's mass as a function of redshift, but the redshift is expressed as a density, it doesn't matter. But if you write the mass accretion history this way, it turns out that the shape of the average mass accretion history of cold dark matter halos is an NFW shape, which looks just like the median density profile, just with a different concentration, which allows you to actually scale one and the other. And so I think the conclusion of this stuff is that these prompt cusps are indeed formed right at the beginning, during the time of peak collapse, but things almost converge in a universal way to an NFW-like form with little dependence on the initial power spectrum and so on. And this is just a natural consequence of universal assembly histories, which I think is itself a natural consequence of Gaussian initial conditions. But that is a hypothesis more than anything else. So why is this important? Okay, this is where I'm going to finish off in 2 minutes, Jan. This is important potentially for dark matter annihilation. Okay. So if we hope to detect dark matter through the annihilation of dark matter particles in the Milky Way or other galaxies, then the expected flux from dark matter annihilation is some combination of stuff to do with particle physics, including the mass of the particle itself, the cross-section for the interaction. But importantly, from the astronomy perspective, I suppose, what is the distribution of the density squared along the line of sight? So clearly, whether your central density profile is -1 or -1.5 and then squared will make a big difference as to how much annihilation you get from these dark matter halos, particularly if there are loads and loads of these really low mass objects, because as we saw from the halo mass function, it becomes really, really steep at the low mass end. So how does this actually look? So this was shown in the Aquarius paper, actually a few years, in 2008. If you consider what the annihilation map for the Milky Way looks in just its smooth component, it's what's shown on the top left. If you look at the contribution to the annihilation signal just from resolved subhalos in the simulation, you get these added contributions on the top right. But then if you extrapolate the predictions from these simulations all the way down to the Earth masses, you get some additional contribution going down all the way to these Earth masses, and you get this total map there. And depending on how much you extrapolate and what you think the properties of the objects are extrapolated all the way down to the end, you can get differences in what you predict to be the boost factor to dark matter annihilation as a result of these small-scale structures that are factors of 2 or more, okay, depending on where in the galaxy you look. So the expected contribution of substructures to the annihilation luminosity in the Milky Way can vary drastically depending on the abundance of these prompt cusps, where they are, how many they are, and what their structures actually is. Okay, so that's why this is important. So these are my conclusions. So we looked at the formation of the smallest dwarf galaxies, finding that they are fossil records of the Epoch of Reionisation, depending also on the assembly of the halos themselves. Semi-analytic models are powerful tools for studying the parameter space associated with these things in a way that hydrodynamical simulations currently are limited in. It turns out supernova feedback is the most influential process shaping the properties of these objects on this mass scales. And hopefully using combinations of multiple data sets, you can study how models respond to different statistics and different predictions to understand galaxy formation better. We then looked at the smallest dark matter halos that could host a baryon themselves, and it's a relatively small mass range, the so-called range of mini halos, and it turns out that the effect of reionization is such that it can actually evaporate the baryons from them completely, and this has an effect not just on their mass assembly history, but also their central density profiles. And there's a certain mass scale below which halos have basically never seen a baryon in their lives. And finally, even smaller dark matter halos, even though they don't contain any baryons at all, they can be seen, but they are seen through their annihilation luminosity. And exactly how much or how clearly you see them depends on what we think the structures are on the inside. But they're also a regime that helps us understand where the universality of dark matter halos actually comes from, starting off as these prompt cusps that gradually converge to an NFW-like shape over time as a result of universal accretion histories. So thank you for your time, and I'll take any questions.